Hi there and welcome to this video for Senior Physics on Electromagnetism and Electricity. In this video we're going to explore the phenomenon of forces that occur in a current carrying wire. This was first observed by Michael Faraday 1791 to 1867. He noticed that when we put two magnetic fields in close proximity to each other, the field lines interact. This interaction can basically cause some movement. Now that movement basically is generated by a force. That force can be utilised in an electric motor or it can be used in the generation of electricity. This phenomenon he termed the motor principle. But what needs to occur or what do we need in order to have the motor principle working? Well, there are two things that we need. One is a stationary magnetic field from a magnet. The second is a current carrying wire. Remember, if a current is flowing, we've got charge which is moving charge generates a magnetic field. So there's our two magnetic fields. But how does this force actually get created? Well, let's look at the scenario below. In this case, what we've got is a wire which is coming out of the page. We can see that because the wire has got a dot in the center, meaning that it's coming out. Remember your arrow scenario that we talked about earlier. Now, using our right-hand grip rule, we can determine the direction of the magnetic field. So it's coming out of the page, our fingers are going to be our magnetic field, our thumb is the current, which means that the field lines around that wire are running anti-clockwise. We now need to place this in a magnetic field. So we've got a horseshoe magnet, which has a north and a south pole, and we can see that the magnetic field lines for that magnet are running from north to south. They're running from left to right. So let's put the wire inside the magnetic field and see what happens. Well, we get a scenario that you can see in the bottom right-hand corner. Below the wire, we're getting a huge number of field lines. Above the wire, there's only a few field lines. Now, why is that? Well, if we look below the wire on the left-hand diagram, we can see that the field lines will be running from left to right. This is in exactly the same direction as the field lines in the magnet, which are running from north to south or left to right. The result is that these field lines construct together. They basically build up a large magnetic field. We have a large magnetic flux or density below the wire. Now, what happens above the wire? Well, again, if we look at the left-hand diagram, we can see that above the wire, the field lines will be running from right to left. This is directly in the reverse direction to that of the magnet. As a result, these field lines cancel out. So we get a diminished magnetic flux, i.e. the density is less. So we've got an imbalance there. Large magnetic field below the wire and small magnetic field above the wire. Now, nature doesn't like this imbalance, and if it's possible to move, what will happen is the wire will be pushed from the bottom upwards until the two forces either side of the wire are the same. As a result, we can see that the direction of the force is going to be upwards, shown by the arrow, and the force is labelled F. Okay, so if we look at a simplified overview, you can see now that we've got the wire coming out of the page. North to south is the direction of the magnetic field, and the result is that the force is pushed upwards. This is due to constructive production of a magnetic field below the wire, diminished or destructive production of field above the wire, and obviously it moves from one place to the other. Where the two fields are running at 90 degrees to each other, that is on the left and right hand side of the wire, there is no force. So if the magnetic field lines are running at 90 degrees to each other, there will be no magnetic force that will be generated. So how can we increase the amount of force that is generated or decrease it depending on what we want? Well, we can increase and decrease the force by doing a variety of things. Firstly, we can get a bigger magnet. Bigger magnet basically means we're going to have more magnetic field strength. So there's going to be more interaction between the magnet and the current carrying wire. We can also increase the current of the wire. This means that there's more magnetic field which is generated by the wire. So again, we've got more interaction or more field lines which can interact. We can also increase or decrease the amount of wire which is subjected to the magnetic flux of the actual magnet. This is the creation of the solenoid. And remember, from what we looked at with the solenoid, by putting more coils together, we basically combine more of the magnetic fields in the same direction, creating more magnetic field lines and a greater or stronger magnetic field. Finally, we can change the angle at which we place the wire subjected to the magnetic flux. If they're running directly parallel with each other, then we're going to get maximum force. However, if they're working at an angle to each other, then the result is we are going to get a diminished force until the magnetic field lines are running at 90 degrees to each other. At this point, there is no interaction whatsoever. No interaction means no force. Okay, so from this, we should be able to build up an algorithm. Now, this algorithm or equation is going to be feeble. F equals BIL sine theta. Now, sine theta basically is the angle which is generated between the magnetic field lines. When the angle is 90 degrees, the result will be that sine 90 equals 1, so the force will be at maximum effect. Now, force is measured in newtons, magnetic field strength B is measured in Tesla, I is the current in amps, and L is the length of wire subjected to the magnetic field. This is in meters. Now, later in this post, I will put up some videos of some worked examples using this algorithm, and then there are some examples for you on a worksheet for you to work through. So that deals with the algorithm, and now we can calculate the size of the force which is generated. We also need to be able to determine in what direction that force is generated, and we've got another hand tool in order to use that. In this case, it's the right hand slap rule. Now, the right hand slap rule works in the following way. Your thumb is going to be the current which is flowing through the wire. Your fingers is going to be the magnetic field of the magnet, and your palm is going to be the slap. That is the force which is going to be subjected onto either charges or to a moving wire. So to reiterate, thumb is the current, fingers is the magnetic field, and the palm is the force. So let's have a go at some examples and try and work it out. So use the right hand slap rule to determine the direction of force of this current carrying wire between the magnetic field. Okay, so this is how we do it. Our thumb is going to go into the page, shown by the cross. Our fingers are going to be running from right to left, from north to south. That means that our palm is facing upwards, so there's a slap upwards on the wire. So the force is upwards. Try this one. Okay, in this case, our current is coming out of the page. So our thumb is pointing towards us. The magnetic field is running from north to south, which means the palm is facing up, which means, again, we've got to have the force going upwards. Let's have a look at this one. So now our current is running in this direction. Our field line for the magnet is running from north to south. So my thumb is running from left to right, my field lines are down, which means the force is into the page. So I've now got a force which is acting on that wire, pushing it into the screen. And finally, we've got one going in the opposite direction. We've got the current going in the same direction, but in this case, the magnetic field is basically running up along the screen, which means our palm is facing me, which means the force is going to be pushing the wire outwards. So I get a force out of the page. How did you go with that? Was that okay? Good. That means now you can determine the direction of the force. Now, this example here I've shown on a video in this post, which basically shows a wire which is suspended between a magnetic field. Now, in this case, we will see that the force is generated and the wire will swing out. But why is that? Well, the first thing we need to look at is we can see the current is running from right to left. So we use our right hand grip rule to determine the direction of the wire. In this case, it's going down behind the wire because it's running in this direction, running down behind the wire and up in front of the wire. We then have to determine the magnetic field, the direction of the magnetic field. Now this is going to be running from north to south, so it's going to be downwards. So now what we've got is running downwards. So anything running down, they're going to combine. Anything running up is going to cause constructive. So we need to look at the interaction between the two fields either side of the wire. So basically, magnetic fields are in the same direction behind the wire, so they construct. but magnetic fields are in the opposite direction in front of the wire, so they destruct. So the overall effect is there's a greater force behind the wire than in front, so the result is the wire is pushed outwards. So check out the practical in this post to explore that. Now we can now talk about the same sort of things when we're looking at two wires which are running parallel to each other. If they're in the same direction, we always state that the force is going to be attractive, i.e. they're going to combine together. If they're running in opposite directions, they're going to be repulsive and they're going to be moving apart. So let's look at these two wires that we've got here. They're both running into the page. Running into the page with a right-hand grip rule means that the field lines are going to be running clockwise. Now let's look what happens inside between the two wires. In between the two wires, you can see that the two field lines are running anti-parallel to each other, and they're in opposite directions. That means that they're going to cancel out, meaning that the forces in between them are going to be a lot less. There's going to be less field lines pushing on them, which means the forces of the magnetic field outside of the wires, on the left and the right of the wires, are going to be greater than inside. The result is the wires will be attracted to each other. They'll be pushed in. So let's look at the opposite side of the coin. So in this case, we've got one current going into the page. We've got one current coming out of the page. In the middle, you can see that the two wires are running in the same direction. They're running in the same direction. This is constructive. This means that the field strength is a lot larger in the middle than it is outside, which means we've got an imbalance of force, strong in the middle, small on the outside. The result is the wires will be repulsive and they will be pulled away. Well, I hope you found that useful. I do hope you have a go at the worksheets, look at the exemplary videos, and check out some of the practical videos that I put down to try and explain this. I look forward to you joining me again. Thanks for